It would also help to compare observations from different locations and different equipment. If another observer captures the same angle changes at roughly the same times, that reduces the chance that we're seeing an artifact of one setup or one processing style. And if the pattern holds across different processing methods, gentle stretch versus stronger stretch, with and without sharpening, that also makes the feature more robust.
There are nights when you take a picture, expecting the usual comet, look a soft head, a faint tail end, you move on. And then there are nights where a small detail refuses to behave the way you expect. Not in a dramatic way. Just enough that when you compare two images, you catch yourself saying, wait, that's not the same. That's what happened here with Comet 3I. Atlas. What made it interesting isn't the fact that it has a tail. Most comets do. What grabbed my attention is a very specific thing near the brighter inner region, the part close to the nucleus. The structure looks like it's producing jets, and the direction of those jets doesn't stay consistent from one image to the next. When the comet is near its closest point to us, you tend to get sharper detail, better scale, and faster apparent changes, simply because the geometry is tight and the comet is moving quickly across the background. So if there's ever a time to notice subtle patterns, it's around a close approach. Let me walk you through what I'm looking at and why. I think it's worth discussing carefully. First, just to set the scene in plain terms, a comet is not a single solid thing with a neat glowing tail attached like a cartoon. It's a small nucleus ice mixed with dust and rocky material, and when it comes closer to the sun, sunlight warms it up. That heat turns some of the surface ice directly into gas. The gas drags dust with it, and the result is a hazy atmosphere around the nucleus called the coma, and then a tail that gets shaped by sunlight and the solar wind. That's the classic idea. But comets don't always release gas evenly. Sometimes the gas escapes from particular spots, little openings, cracks, or weak areas. When that happens, you can get jets. Those jets can look like narrow spikes, curved fans, or faint smoky arcs, depending on viewing angle, exposure time, and how the comet is oriented relative to the sun and Earth. Now, here's the key. When you image a comet, you can look at it in two different reference frames. Even if you never say it that way out loud, if you align images on the stars stay sharp, and the comet crawls across the frame. If you align images on the comet stays centered and the stars streak. The second approach is usually better when your goal is to study the comet's own shape, because you're not constantly chasing it across the screen. So, imagine we've taken a sequence of images over several hours. In the wide view, it might look like a slightly elongated streak with a faint tail. It's pretty, but it doesn't tell you much. The real story shows up when you crop tighter around the comet and look closer at the inner coma, the brighter region near the nucleus where any jets would originate. And this is where the pattern starts to show itself. When you flip between two frames that are very close in time, the outer tail might look roughly similar, because that's a large-scale structure and it doesn't always change dramatically minute to minute. But near the inner coma, there's a sharper feature, almost like a brighter edge or a concentrated plume that seems to lean in one direction in one frame and then shift in another. It's not just fading or brightening. The apparent angle changes. The direction of the feature looks different. If you've ever tried to compare faint details in space images, you know how easy it is to fool yourself. So the first thing I do is try to make the comparison unfairly strict. I don't stare at one frame for a long time and then trust my memory. I flip back and forth. Your brain is actually better at seeing differences when it's allowed to compare directly instead of reconstructing. That quick alternation makes the angle change stand out more clearly. Then, I try a few basic checks that don't require fancy science, just patience. I'll look at the same area at the same zoom level. I'll keep the contrast similar. I'll avoid overcooking the image, because extreme sharpening can invent edges that aren't truly there. And I'll check whether the feature persists if I slightly adjust the stretch. If a structure only appears at one very specific processing setting and disappears if you breathe on the sliders, that's a warning sign. But if it holds its shape across a reasonable range of processing, it becomes harder to dismiss as a processing artifact. In this case, the feature I'm focused on appears persistent enough to take seriously. And the most interesting part is that the change can be noticeable even between frames that are close together. Now, let's slow down and think about what could cause that. And we'll start with boring natural explanations first, because the universe is usually weird in a normal way. One obvious possibility is rotation. If the nucleus is rotating and one active region is venting gas like a nozzle, then the direction of that nozzle, as seen from our line of sight, can change as the nucleus turns. You don't need anything exotic for that. You just need a spinning, irregular object with a vent. If the rotation period is short enough, or if the vent is near a region of the nucleus that gives us a strong visible effect, then a jet can seem to swing. Sometimes it won't look like a smooth swing. It can look like it jumps because we're not seeing a rigid rod rotating, we're seeing changing brightness in a cloud of gas and dust that's expanding outward. Some parts get brighter, some fade, and the visible edge can move. Another natural possibility is that there are multiple vents. Imagine two weak spots on the nucleus. In one moment, one vent is sunlit and active, producing a brighter jet. A short time later, due to rotation or slight changes in illumination, that vent weakens and another vent becomes dominant. The result can look like the jet switched sides or changed direction, even though what's really happening is a change in which vent is contributing the most visible material. A third possibility is geometry and perspective. When a comet is near a close approach, the relative angles between Earth, the comet, and the Sun can change quickly. The same 3D structure can look different when projected onto our 2D image. A jet that is actually directed somewhat toward or away from us can appear narrower, shorter, or shifted depending on perspective. If the comet's orientation changes a little, or if our viewing angle shifts enough, the projected angle of the jet can look different even. If the jet itself hasn't physically rotated a huge amount in space. Those are three decent possibilities: rotation, multiple vents, and perspective. But there's also a fourth category we have to respect, because it's the one that ruins many exciting claims: Earth-based imaging issues. The atmosphere is not stable. Even on a clear night, the air is moving and it smears tiny details. That's what astronomers call seeing, but you don't need the term. It's just turbulence. Some frames will look sharper than others. Slight focus drift can make a bright edge appear to lean or thicken. Tracking errors can smear the inner coma in a particular direction. And processing choices can exaggerate edges and make a faint gradient look like a crisp jet. So the honest approach is to hold two thoughts at once. 1. The angle change looks like a real pattern worth watching. 2. We need to be careful not to confuse persistent in my processing with certain in physical reality. Now, here's where it gets interesting again, because even if some of these effects are partly responsible, the fact that there's a structured inner coma at all is still meaningful. A featureless comet would just be a blob and a tail. When you begin to see defined shapes near the nucleus edges, fens plumes, that's telling you the outgassing is not uniform. Something about the nucleus surface is directing material in particular ways, and that leads us to what I think is the most fair: open-ended interpretation. This comet appears to have localized activity that produces structured outflows, and those outflows can change in appearance on short time scales, as seen from Earth. That's a careful statement. It doesn't claim a mechanism with certainty. It simply says the pictures show structure, and the structure changes. If I had to rank the possibilities purely on what usually happens with comets, I'd put rotation and multiple vents at the top. Those are common, and they fit the idea of jet direction changing without needing anything extraordinary. Perspective effects are also likely, especially near a close approach when geometry changes quickly. And atmospheric or processing effects are always in the background as potential contributors. Now let me add one, more subtle possibility. And this one is still natural. Sometimes what looks like a single jet is actually a combination of dust and gas components. Gas can glow differently than dust scatters sunlight. Dust can form broader fans. Gas can appear more filament-like in some conditions. Depending on filters, exposure times, and the comet's composition, a jet might not be one single thing. It might be layered structure, where different parts become visible at different times or processing levels. That can make the inner coma look like it's reshaping itself. Now, I want to pause and be very clear about something, because it builds trust and it keeps the conversation grounded. None of this proves that the comet is artificial, controlled, or anything like that. It doesn't prove there's a machine inside it. It doesn't prove there's intelligence behind the behavior. Comets are chaotic natural objects, and natural physics can create patterns that look surprisingly organized when you catch them at the right angle and the right time. What the images can do, if we treat them honestly, is highlight a pattern. A structured feature near the nucleus appears to change direction or shape between frames. That's it. That's the claim. Everything else is a discussion of possible explanations. So what would actually clarify this? The best thing is more data over time, especially a long, consistent sequence. If the jet angle changes in a smooth, repeating cycle, that would strongly suggest rotation with an active vent. You could even estimate a rough rotation period if the pattern repeats reliably. If the jet seems to alternate between two preferred directions, that might hint at multiple active regions turning on and off. And if the changes correlate with the comet's orientation relative to the sun, like certain structures appearing when a region rotates into sunlight, that also supports a natural illumination-driven explanation. It would also help to compare observations from different locations and different equipment. If another observer captures the same angle, changes at roughly the same times, that reduces the chance that we're seeing an artifact of one setup or one processing style. And if the pattern holds across different processing methods, gentle stretch versus stronger stretch, with and without sharpening, it also makes the feature more robust. Another useful piece of information would be changes as the comet moves away from the close approach. As distance increases, the comet will shrink in apparent size, and fine structure becomes harder to resolve. But the geometry also changes. Sometimes a jet that looks dramatic at one angle becomes subtle at another. Watching how the structure evolves with changing perspective can tell us whether we're looking at a rotating source, a stable fan, or something more complex. So for now, I'd summarize it like this. This comet gave us a window where inner details are visible, and when you compare consecutive images, the jet-like features don't sit still. The careful move is to keep observing, keep comparing, and let the pattern reveal itself over a longer run, instead of forcing a conclusion too early. And if you enjoy this kind of slow, evidence-first sky watching, consider subscribing so you don't miss the next set of observations.